So welcome all again for this Thursday's NanoSpin-off talk that are organized by Cátedra Sanca of Nanotechnology. Today, we are really glad to have Alexander Legant for a company that I would say this is NanoSpin-off, but that was a long time ago was NanoSpin-off. Now it's a clear spin-off company that grew up. So they are in the market since 2007. That was the starting point. So this 20 years after, Alexander was from the very beginning. No? Okay. 2014, maybe, or
2011.
11. Okay.
10.
10. Okay. So he is a physicist, studied in Darmstadt and Heidelberg. Okay. And he will explain us about these microfabrication tools developed at Nanoscribe, which are really amazing. Jose Maria knows about the tools. I think this is a tool that we would like to have, but we have to think on the money that cost. But of course, it's an advancement for an institute like us that is working in nano and microfabrication. So he will explain us the process of the photography and all the things that they have developed in this company. So thank you, Alexander. The floor is yours.
Thank you very much for the introduction. And I also will repeat a few of the words here then, just by introducing then the company. So I will say something about then how what we do is then can be used then for design of 3D materials, for additive microfabrication on with submicron feature sizes. So this is typically what we produce, what you see here, these type of machines here. And so these are microfabrication machines and for possibilities of submicron feature sizes. And there are different names to address it. For example, in the past, we said these are 3D laser lithography systems, or in general, you can say it's additive manufacturing. And so these machines then provide a high variability then of designs, of materials, of solutions then to work with. And also then with different materials. So some words about the company. So you already heard about that we are now, more than 18 years old, 100 persons in the meantime. I started around end of 2010. We have offices because these are then, you see them more or less then, we have last year, so our markets were quite equal between Asia, Europe, and the Americas. And that's the reason why we also have then, of course, since a while then offices in US and China. And we are a spin-off from a German university, the Karlsruhe Institute of Technology. So at the beginning, the company Zeiss, for example, had some shares. And then so we were also owned in between by a few years then by the Swedish company BICO. And since November 24, we belong to a German foundation, the Lab 14 group. And what you see over here, by the way, is then so we are located in these two ground floors. We just occupy most of the space of these two ground floors then with production, R&D, service offices, and so on and so on. So we grew quite a lot over the years with 25 million euro revenue then in last year. So most of our customers are research centers, universities, for example, but more and more, for example, especially last year, we see that there's also definitely some interest from industry that people produce then here, use the system as tools for prototyping or for manufacturing. But what you'll see as well then for then just publications. So you see then here a big increase of different publications also on covers here, for example, like Science or Nature and so on and so on. So around, if you see then here, we have then more of 400 systems now sold and with different platforms. Meanwhile, 9 of them in Spain, just to give you a number. So different possibilities, what you can do with the equipment. So for life sciences, people print, for example, then 3D scaffolds, seed cells on them. You can do here for lab on a chip systems like what you see over here. You can print fine details inside like valves, like pillars, like cell cages, to what you see over here, to seed cells on them, place cells on them. You can print microfluidics. Here you see some examples then just of vascular model, for example, then yeah, some collections over here. People print, for example, microneedle arrays to replicate them. And here we see some examples then for materials engineering, MEMS in this sense. But we came out of the field more micro-optics, photonics, what you see on the right side, microlens arrays. Or what we see at the moment is then that Europe spends then some via the European Chip Act and as well in Spain as well, via the Spanish Chip Act, then some money to finance foundries just to increase then the improve the research then in the direction of so silicon chips, for example, or other types of chips. Then here for photonic packaging, that you just instead of silicon and copper connections, you go directly into optical just communications. And here we provided a technique to do automated printing of here edge coupler elements or optical coupling elements. So this is, for example, how it looks like. So you print here such a surface coupler, or you print here a lens to guide signal out of the plane, and just to have 3D structures to print 3D environments. Here's an example for an edge coupling. You can use the system for prototyping, for mastering, print a microlens array, use nanoprint lithography, for example, to replicate it, or microinjection molding. Or you can also print here directly manufacturing lenses on optical fibers. And we have also some customers who just earn money with it, who offer, for example, the printing of these type of devices then as a print service. So this is how it looks like to provide then here different chips and to print here these parallel lenses. For example, what the system is doing then, that it looks automated, and here for the inner core of, so the illuminated core of the optical fiber, print lenses on top, measures the tilt, for example, automatically corrects then the STL mesh of each lens to have then at the end parallel lenses and then therefore parallel outputs of the laser beams. You can also print here edge couplers. We use a pattern then that you compensate. Of course, you focus from the top, but of course, if you do edge coupling, you have some shadowing effect directly at the edge, and we compensate directly here the laser power to have here always sufficient laser power to trigger chemical reaction. And like what we see over here on the right side, that you work them sometimes with whole wafer levels, with whole wafers, and print directly the optical elements aligned and automated on these type of wafers. More examples here from life sciences, how it looks like. So a model, for example, then for a vascular system, so for its connection, and then here also in more focused, more fine detailed. What you also can do is then that you can play a little bit with AI to vary here the pore size, to vary here the density of these different cubes that you see over here, seed cells, and here's an example of a bigger filter element, and as well then again with anchoring points then for cells inside a microfluidic channel. So more details are given on our website. So if you would like to read more about it, then about here, for example, the industrial scale-up, the master and replication. I will now also give some words about the principles behind what we use, two-photon polarization, and also the next step, then the two-photon grayscale lithography. So if you just here look on the lights on the left side, and for example, if you use a blue laser light, we focus with blue into fluorescent dye, you see that the fluorescent dye shows fluorescence on the whole way of the laser through the material itself here. Now, the thing is then if you go to longer wavelengths, like for example, near infrared, most of the volume, nothing happens, except here at this tiny spot here at the laser focus. And the reason for that is that one photon of near infrared doesn't provide enough chemical energy to trigger chemical reaction, or doesn't provide enough energy to trigger chemical reaction. So what you need is then you need two photons at the same time at the same place. And the probability for that is only high enough than here at the laser focus. And if you exchange now the fluorescent dye against the monomer, then again, the same happens here on the left side of a blue or UV laser then, that if the laser power is high enough, then polymerization, or the dose is high enough, then polymerization takes place in the whole volume. But here on the right side, again, polymerization takes place here only at the focal plane at the laser focus. Now what we do is then that we provide then that we can use two different types of autofocus to find a starting point in Z direction. And so like one is using then here the reflection from the interface between resin and substrate. The other type of autofocus can use the fluorescence then inside the material. And then, so we like this, we define the starting point in Z direction. And by now moving then using two coupled cover scanners, we can just scan along one layer. Then afterwards, we move in X, Y, and Z to just expose one area after the other. Afterwards, the sample is removed from the system, put into a washing bath, monos are washed out, and you have then at the end your freestanding sample with some examples what you saw before. Now the next step forward would be just did is then we use as well here the two-photon grayscale lithography. We have a patent on that. And if you just look at what happens at the laser intensity level, at the voxel level, so then polymerization takes place only if you exceed the laser intensity here, exceeds a certain polymerization threshold. And this area here in bright blue, for example, corresponds to a polymerized area here shown on the right side. The volume that is exposed is called volume pixel or short voxel. Now, by increasing, decreasing the laser power, we can increase and decrease here the voxel size. What you see then again here with some more examples, and if at the same time you scan along one line, you can very nicely follow such a trajectory here, so such a curve then for smooth surface roughness then of microlenses, or for example, the side of microfluidic channels. So the standard approach would be then that you, The standard approach would be then that you just expose one layer after the other and resulting in some staircasing, what you see over here. You can, but you don't want to have that, so you want to have a smooth surface roughness. So you can reduce this staircasing effect by embedding more layers, by decreasing the slicing distance, what you see over here. But this goes hand in hand, and of course, with increased printing time. The more layers you have, the more time you need. And that's the reason why now you can use here, we use this two-photon grayscale lithography, 2GL, and have still quite big layers that we expose, and just use here the 2GL effect on the side here at the slopes, and to have then the same speed like with big steps, but at the same time, then also surface roughness is going down to around 10 nanometer. And typical example then for 3D printing technologies is here this Benchy boat. And on the right side here, you see then if you just do one layer after the other, you have here again, you see at the surface, you see this this steps in between. Sorry, the steps in between, and what you see as well then here is then of course here's some undercuts. And now on the left side, we use this 2GL effect also in 3D, 3 dimensions, also for undercuts. And the left side, with nearly the same speed like on the right side, you get then smooth and nice just output here. And this works on different scalings and different resolutions. So to print on different size scales, to print different resolutions, we take different objectives. We say typically we have some printheads for SF small features, medium features, large features, and extra large features. And what you see here so with the staircasing and with the smooth surfaces, this works on just different scalings. Here on the right side, we just did it for some testing. But this here so these three are standard then for that we deliver then as software to our customers if they like. And just to give you an idea what different scales I'm talking of, so this is here then really also different sizes. And that means, of course, then that, of course, before for other 3D printing, for coarser 3D printing techniques, the Benchy boat was a very nice benchmark. But yeah, here's just standard that you can print it. So I said in between, we use an autofocus to find the interface in Z direction. But as well, then we use here as well then a confocal module inside then to find as well then to measure here steps, like for microfluidic channels or for photonic integration. And like this, we are as well able then to find starting points in XY direction, markers, crosses, for example, then to align then the printing system, the coordinate system is X, Y, and XY. And so typical applications are print on optical fibers. I said a bit about before that. So you find here then as well in XY direction, you look for the illuminated core. You look here for chips. Typically, you have these type of markers over here. Look very often here like these rectangles here. And then you define, so in which distance of these is the waveguide. So this blue thing here is the waveguide. So theoretically, without any optical element, you would see here the signal orange just getting out of the waveguide quite angled, inverted. But of course, that means if you would like to cover that somewhere in, you would have very big losses. That's the reason why I just print here such an optical, so an edge coupler, an optical coupler, have a parallel beam to be able to couple it in somewhere else. And as well, then of course, you can print directly at the surface then on a wafer. What materials then are we work with is then, so what is the principle behind this then two-photon polymerization? That means typically as a standard, so there are different ways, but let's say as a standard, you get a polymer. So most of our proprietary resins are acrylic-based resins, like what you see over here. But the system is open in terms of materials. By the way, I can send you later on the slides as PDF file, and then you have still the pictures. And but for example, you can bias them. So these epoxy resins, so this is SU8. Positive tone assist means, so before I showed you start with a monomer where you expose to get a polymer. Here for the positive tone assist, it's the other way around. You have a polymer. With the laser, you break up the bindings. Then later in the washing bath, you wash out then the monomers. Means more or less you create here these type of gaps or these edges in between. Very often in life sciences, here an example for muscle cells, you work with softer materials, with hydrogels. Then you can also mix the resin then with particles. So you see here some composites. And very often, so I would also show some slides more about that, that you start with the polymer to use it as a template. And here in this case, this here was using electroplating to get here gold structures, gold helical structures. So for examples then from external companies, so then here bioinks, they provide then for life sciences, then they provide, typically you want to have softer materials, so hydrogels like gelatin, collagen, HA for example, then to seed your cells in them. So you can buy them directly from here from the company bioinks. And advanced materials then, for example, so both of these. Resist Technology is another material provider. Or here for Glasomer, oh yeah, we'll just show them. So Glasomer, you can also get glass. So as an example, what we for one of our proprietary materials, PDMS, you see them here that you can print soft and flexible elements. So shown on the right side and compared to one of our standard materials here on the left side. You see here, so typically, you measure this by the Young's modulus. The Young's modulus here on the right side is around 15 megapascal, and here it's in the gigapascal region. So that's typically a factor then, yeah, let's say 50 for, no, 50 around. And you see then, of course, this here is very flexible, and this is much typical material, polymer materials, and much more rigid. And the same is, of course, valid then for cells. So on this rigid material here, with a bulk material, you only want to seed bone cells. So this here, the thickness here corresponds to cartilage, but also by changing the laser power, changing the size and hatching, you can adapt as well the Young's modulus, that you can seed also other cell types of them, or you can print micropillars, that you can also seed then brain cells or retinal cells in them, for example. More materials. So as mentioned, so I showed before Glasomer, so you can buy then these type of print sets here with a few silica nanoparticles inside. After 2 baking steps, you get from via the brown and green part, then from left to right, and get really fused silica cloth. But here from left to right, you have also shrinkage of 35%. It means typically you only do that for bigger structures, for medium-sized structures. And not to forget then, so here we see some gold examples by electroplating. So what you do typically is then you start this with a positive tone resist here. That means you start here with this block. You exposed here these helical structures on a conductive layer. Afterwards, you put this here the sample into an electroplating bath, and the gold here structures then did rise, and of course you stopped at a certain point. And after burning away here the outer polymer, you had here the freestanding gold helical structures. Or always, so what you can also do is then you can do 4D printing, and 4D printing means that you have reaction, for example, over time. And you can also design your materials either by chemical structures, or very often is then that you have a so-called optical metamaterials, mechanical metamaterials. That means depending on the unit cell you choose, you have different results. So here, for example, what they did is then they started with a polymer structure, coated that via LD, atomic layer deposition. And here another example from the same group from KIT. And typically what they want to have is then they want to have a strong material, but light material. And so what they typically do is then that they here press from the top, measure the force that they need to destroy such a structure, and then they divide it by their own weight and had a better ratio than so compared to, for example, the bulk material steel. And there are more people just, for example, using electroplating to have than other types of these of measures. Then the idea is then, for example, to use such an element then for battery research, to fill it with lithium ions and so on, with silicon and so on and so on. Another material then for mechanical metamaterials. So here, if you print such an element and you press from the top, then so the element just also the side walls move into the structure. Of course, this is the opposite thing that you would do like for the bulk material. So you have then here a negative Poisson ratio material. Another example for mechanical metamaterial, here it's due to the design of this unit cell. It's here like if you press now from the top, you get some twisting effect. And so here another example then, just to give you some ideas of this so-called pentamode structure. So if you transmit some acoustic waves through it, it behaves more or less like a fluid. And just to give you some ideas then about size scales, you see here 300 micron and here 20 microns. So a Middle European hair, the thickness of a Middle European hair should be around 80 micron, for example. And here small d, if I remember well, was in the area of 500 nanometer. So you can go down here to sub-micron feature sizes. The same group here so it was one of our founders, so Martin Weger's group. Sorry, they had some time ago, they had an invisibility cloak. That means if you just guide it with some light into an element, it was guided, so it was guided around. You could not see an obstacle underneath. Here's the same with a mechanical metamaterial. Means if you press from the top, the force is guided around. You cannot feel here the obstacle underneath. And the authors then during that time had a very nice sentence then that they said, so this would have been the solution in the fairy tale of Hans Christian Andersen. So for the princess on the P. So the P, of course, was on all the mattresses, and he said, oh, it's so horrible, I cannot sleep very well. So this would have been the solution, and she would have been relaxed and refreshed in the morning. And so some people want to have movable elements. So you see here some crapper, from Borapur, from Imperial College London during that time. And what so some people also did is then that you can print these type of cantilevers, and you can print, for example, also longer cantilever tips than, for example, if you would like to do AFM then for some deep valleys, that you can also go below to the ground more deeper. There are some people just working with movable elements. And so, for example, what you see here, magnetically actuated micro-robots. So there are different ways of trigger a movement, like chemical reaction. In this case, it's magnetic reaction. And the idea behind is then that you print such an helical structure. coated with nickel, and then put it into a changing electromagnetic field. And just due to the form, it reacts and you have a movement along the main axis. And like this, so here, so Maria Medina Sanchez, for example, in that time in Dresden, now she is in San Sebastian, just used here this type of motor, then as an outer motor, so use this micro-robot then as an outer motor for such a sperm cell to deliver it to the oocyte, for example. And also, by the way, they did coat with titanium, because the idea, the principal idea very often is then you would like to enter trucks here and put them into your blood veins then and arteries then to move these type of microbots automatically, autonomously then to truck cell that they could detect, they could detect cancer cells and directly destroy them. But for that, you would need much larger numbers. That's one thing. And not to forget, of course, then nickel, you don't want to have nickel in the human body. So there was also other work then from here, the crew of Brett and Nelson for the ETH Zurich, where they mixed hydrogel with then super biomedical nanoparticles then, and also to have not only biocompatible, but also biodegradable material. At least that's what they said in the publication. I think it was not this degradable, but okay. And what you also can do is then you can use this technique to change surface properties. So what you see over here. And also you can also replicate these type of design with an undercut. And so like what you see over here. So then here it was printed, and the original design was printed in front of the our standard resins, replicated via PDMS then to mold to get here this the other structure, this other material. And like this, you could have here used this type of pick and place tools. Or some other work is done. So it's a lot of work is done with mimicry, with just here copying structures from nature. On the right side, you see here a picture of the Salvinia plant. The Salvinia plant, if you look here on the microscope, then here for these type of elements, they have hydrophilic parts here at the top and hydrophobic parts underneath. And the Salvinia plant just grows in flooded areas or in areas that are often flooded. And then, so what's happening is then that the hydrophilic part here on the top attracts the water, but some air layers caught underneath. So the water is just prohibited and is just prevented from directly attaching here the plant itself, the stem. And like this, it can survive and you prevent molding, and the plant can survive much longer than in this type of environments. And now, just around 100 times smaller, they copy this type of design. And now it's just about this here, the chemical reactor, so chemical purpose here, chemical property. And this is just the physical property that if you place here some water at the top, it is just kept away from the ground via the surface tension. And also, of course, you want to have that vertically then over a larger area then, for example, perhaps to use it then on some boat elements then to reduce friction on water. But yeah, that would be a long way. So what you also see is then that people mix elements inside, mix materials, and then you see then some 4D printing elements, means depending on which type of temperature, so sometimes temperature or chemical reaction you provide, you can, for example, dissolve elements, add elements, so more or less, yeah, dissolve elements. In this case here, you trigger then some increase of the size over the time. And at the same time, you also reduce then the Young's modulus, make it softer, and or increase it in, for example, and what you see over here, depending on what chemical reaction you just place here. Work from Eva Plastics group from University of Heidelberg. Or I showed that before already, so some micrometer arrays then over a larger area, and some. You can also have centimeter output, but if you are only interested in this type of bigger elements, normally you would go to another technique. So here it's just a little bit an add-on just to have that be able to do as well than here centimeter printing. Some more ideas then, you can also do multi-step printing, multi-material printing. So for this type of steps then, it's about mixing different materials then to fine tailor your environment and for your cells, just to focus, to be able to control where they adapt to, for example. And also, if you want to print into existing microfluidic channels, then you see then that you can print here, so some nozzle elements inside what you see over here. And so therefore, you need typically micrometer precision for the alignment, or then also if you work here to place such a fiber inside, or an optical coupling element. You see here again in here these type of markers that you use. You need them more in the submicron precision. So this is an example then made from my colleague. So he first printed an biocompatible material like here this PECTA, what is very often used then for cell seeding. And then he placed in another material, then a more rigid material, and here the IPS, and align them according to these type of elements. And this is how it looks like then, for example, then in the program for job preparation. And this is how it then looks then after the first step in real life, after when you just here examine then the different materials, or the output. And this is how it typically looks like then during the printing. So the second step is printed on top of the first step. You see here, for example, the laser, how it moves through the field and exposes then one area after the other. And then, so on top of the first area underneath, you also see then that the second area was added on top. And also this then on a larger scale. So here's some other work then that you work with different types of materials. And so the cells like this, you could control where the cells go to, shown in orange then some with some coated protein material. And then you see that the cells only connects to there, but doesn't want to connect here to the other part. Like this, you can just measure forces, increase it, and so address some stress onto the poor cell. More information is given on our website. For example, so I said already before, then the white papers. So this is in our, you see then also some webinars, our so-called premium section. So if you look for Nanoscribe premium section, you see then this more of this work is shown in these webinars here. We also invited some guests then to show more about their work. And by the way, I just showed multi-material printing for that you provide one material. You remove typically the sample from the machine and then just apply some washing. And then you put it again back for the second print step inside the machine. So here the company Heteromerge, they provide as well then an add-on that you can leave everything inside the machine, and it's automatically exchanged in the material then via this add-on. So that brings me to the end. So thank you very much then for your attention. And sorry, and do you have questions?
Impressive. It means that can be every material, every size, every type can be done. Because I didn't know that you also have to part of the ALD that can give many different materials on top of that. But this is a question. No? This is in collaboration. You can also do that. You work as selling the machines, but you can be also a service.
So we sell the equipment. Some of our customers do print service. So and different levels. So very often it's like this. If you know someone who owns a Nanoscribe machine, we have different models outside. We have different platforms outside. Then you might be able to use the system directly there. That's one thing. The other thing as well then that you can as well then order elements. So for example, then the printing of the lens on top of optical fiber. There's just one company, the company Fix in the Netherlands. They provide print service for that, or for these micro-lens arrays, or then stacked lenses and so on. Then on optical fibers, so there's a company called Print Optics in Germany. They provide print service as well.
So because right now, you mentioned that in Spain we do have like 10 or 9. Okay, and in Europe, or how many how many of these machines are around?
So worldwide, it's more than 400 sold. And to be honest, I'm not totally sure. I think in between we had half. So many years ago, let's say a few years ago, we had half of the systems in Europe, but then US and China got stronger over the last few years. So yeah, it's somewhere between third, and a little bit more perhaps than still in Europe. Yeah.